right, so let's take a few minutes to review the assigned end of chapter questions and problems. So we'll start off with 3 review questions, page 459, problems 2, 5, and 6. So this question is asking if you have astronauts walking around on the surface of the moon, which many years ago we did, why must astronauts communicate by radio when they're on the moon? So we know that sound requires an elastic medium. So on the surface of the moon, we don't have an atmosphere. It would be a vacuum. So the sound would not travel through the vacuum. So if they're walking around on the moon and they have their spacesuits and their helmets on, they would be talking by radio. And as we know from chapter 33, radio waves, along with all the other types of electromagnetic waves, do not require a medium. So they'll travel okay. So the question goes on to say, can they hear another spacecraft as it lands nearby? So here's another spacecraft landing nearby as they're walking around on the moon. And of course, we have the same answer to that one, is they would be able to see the other spaceship landing, but they wouldn't be able to hear it because the sound, any sound made by the spacecraft would not travel through the vacuum. All right, so, and then the last part of that question is, can the 2 astronauts hear each other by touching helmets? So what we're suggesting here is, what if their radios stopped working for some reason and they still wanted to talk? Could they walk up to each other and touch their helmets together and talk and hear each other? So the answer to that one would be yes. We're assuming the helmets are made out of elastic material, some kind of combination maybe of plastic and metal. And as we discussed earlier, back in chapter 13 with elastic materials, there are very few inelastic materials. There are some, but anything that the astronauts would be wearing for helmets would be elastic. So, and we're also assuming that in order to breathe, there would be air inside their helmets. So sound would be able to pass between the helmets if they were touching, and they might be able to hear each other. The next question is question 22.5. So in this question, they're suggesting that you want to estimate the distance to a thunderstorm in miles, and they're suggesting that you can estimate the distance in miles by counting the number of seconds between noticing the lightning and hearing the thunder, and dividing the result by 5. So the question is, can you explain why this is a reasonable approximation? So we've already talked about this earlier in the chapter, but let's go through this again. So distance to a thunderstorm in miles. So we have to make some assumption. Let's make an assumption that the air temperature is about 75 degrees Fahrenheit, which is a reasonable number. And in order to use our equation for the speed of sound in air, we need Celsius temperature. So 75 degrees Fahrenheit is equal to about 24 degrees Celsius. We talked through how to convert between Fahrenheit and Celsius, so we don't need to go through that detail. You can do that on your own. But 75 Fahrenheit is about 24 degrees Celsius. So then we can use our speed of sound in air equation, 331 meters per second plus 0.6 times the Celsius temperature. So let's substitute the 24 in there. And if you do that calculation, you get 345.4 meters per second. So we have the speed of sound in air. However, we're asked to estimate the distance in miles. So we need to convert the speed of sound and air in metric from metric to English. So let's do that. So 345.4 meters per second. And you have a conversion on the inside cover of your textbook that tells you there are 3.281 feet per meter. So that gives you approximately 1,133 feet per second for the speed of sound in air at that temperature. All right, and one last step. So now we're going to apply the speed equation, the general speed equation. Speed is equal to distance divided by time. So you're asked in this case if 5 seconds is a reasonable estimate for the speed of sound to travel a mile. So we're going to solve this equation for time. So time is equal to distance divided by speed. 1 mile is 5,280 feet, and the speed of sound at this temperature is 1,133 feet per second. So you're left with seconds. So that calculation gives you about 4.66 seconds. So I think we can answer that question and say that yes, dividing by 5 is a reasonable approximation. It's not exact, but it's reasonable. And the next question, 22.6. So you're given two different situations. A store window is broken by an explosion several miles away. And then another scenario is a glass of thin crystal shatters when a high note is reached on a violin. Are the causes of damage similar, and what physical property was responsible in each case? So here's our table of sensory and physical properties. So the first one you probably could answer in two different ways. The more likely cause of the store window breaking due to an explosion would be intensity. Remember we said intensity was power divided by area. If you had an explosion which was violent enough, then that power could be transmitted, and just the sheer power of the explosion could cause glass windows to break. Could it have been the specific frequency put out by the explosion? Possibly, but I think this question is suggesting intensity. The second scenario, a glass of thin crystal shatters when a high note is reached on a violin. We talked through the section on forced vibration. So this statement is suggesting resonance, where the thin crystal likes to vibrate at the same frequency that was put out by the musical instrument in this case. So we're probably talking about the frequency being put out by the violin causing the crystal to shatter, not the actual loudness or power being put out by that sound from the violin. Now let's run through a few end-of-chapter problems. Problems 16, 17, and 21 back on page 460. So on these problems, you're being asked to calculate the intensity level of a sound in decibels given the intensity in watts per square meter. So here's the first one, number 16. You're given that a sound has an intensity of 4 times 10 to the minus 5 watts per square meter. And what does that correspond to in decibels? So we have our equation, intensity level in decibels is equal to 10 times the log of the intensity divided by the hearing threshold, which we know is always 1 times 10 to the negative 12 watts per square meter. So what we're going to do is substitute our given intensity into the numerator. And you notice that the units cancel out, and when we're done we'll have decibels. Okay, so there's several ways you can do this, and everybody's calculator here in the room, most of them are different, so you're going to have different methods. If you can manage to keep track of the powers of 10 in your calculator and do this calculation, that's great. If you're having difficulty with it, you can use your exponent rules from math. So if you were to take the 10 to the negative 12, flip it up into the numerator, then that becomes 10 times the log of 4 times 10 to the negative 5 plus 12, and that ends up being 7. So you're taking using your calculator, take the log of 4 times 10 to the 7th. And once you do that calculation, you end up with 10.
Good afternoon. May I have your attention, please? Kelsey Rue and Courtney Sadowski, could you please go to DMS and pick up your hoagies whenever you get a chance? Kelsey Rue and Courtney Sadowski. Hoagies are at the DMS building.
All right, don't everybody run to the DMS building. This happened a few days ago. All right, so this ends up being 7.6, and then you multiply by 10 to get 76 decibels. All right, so that is number 16. Now let's go over number 17. So 17 is giving you an intensity of 6 times 10 to the minus 8. Watts per square meter. Substitute that into our equation. Okay. Once again, if you want to do the exponents manually, then this would become 10 times the log of 6 times 10 to the minus 8 plus 12, which ends up being 4. So take the log of 6 times 10 to the 4th and then multiply by 10, and you will get 47.8. Decibels. Okay. But once again, if you can figure out how to handle the exponents in your calculator, then that's fine as well. All right, and then one more, number 21. So 21 is the same kind of problem, but for some reason this one is just putting 3 calculations all in one problem. So you're giving 3 separate intensity levels, 1 times 10 to the minus 6, 2 times 10 to the minus 6, and 3 times 10 to the minus 6. Now the only one thing that's kind of interesting about this problem is that if you look at the answers in the text, 60, 63, 64.8, that gives you a real sense for what we discussed concerning logarithms, as logarithms takes a big range of numbers and squeezes them down into a much smaller range. So you can see that the difference between 60 and 64.8 doesn't appear to be that much, but the difference between your given intensities, 1 times 10 to the minus 6 up to 3 times 10 to the minus 6, the 3 times 10 to the minus 6 is 3 times as intense as the 1 times 10 to the minus 6, but you don't have a factor of 3 dividing those 3 answers. So there you can see the effect of the logarithm function squeezing down those intensity levels in decibels. So we don't need to go through those, but you can work that problem to verify that you're getting the same answers. Okay, so I want to go over one more problem here. Let's do a problem where instead of being given the intensity in watts per square meter, here's a problem where you're given the intensity level in decibels, and then you're asked to calculate the intensity in watts per square meter. So let's take a look at number 18, also on page 460. So in this case, you're given that the intensity level is 60 decibels. And you're asked to calculate the intensity in watts per square meter. So we have our basic equation. Okay. And so in this case, we're solving for the intensity, and we know once again the hearing threshold is 1 times 10 to the negative 12 watts per square meter. And in this case, we're also given that the intensity level was 60 decibels. So we're working this kind of in reverse. So the first thing you would do, we're going to manipulate this equation using algebra. You're going to divide both sides of the equation by 10. $60 divided by 10 is 6. Then we also discussed the fact that the log, base 10 log, has an inverse function. And you can see that on your calculator, and that is the 10 to the x function. So we're going to apply 10 to the x to both sides of the equation. So what happens on the left is 6 becomes the exponent. So the left side becomes 10 to the 6th. And when you apply 10 to the x to the right side of the equation, it causes the log function to go away. Similar to the effect you get, when you have the squared function being the inverse of the square root. So it's the same kind of idea, right? And then you have another step here. So now we're solving for the intensity. So the intensity then is equal to 10 to the 6th times your 1 times 10 to the negative 12 watts per square meter. You could just call that cross multiplying. And you notice that you do have the correct units. So this ends up being 1 times 10 to the minus 6 watts per square meter. Because when you multiply the 10 to the 6 times the 10 to the negative 12, you're just adding the exponents together. So it's 6 minus 12. And you can do further practice. I'll leave you with problem 22.19, where you can practice the same kind of problem, this time given a 40 decibel sound.